Hello teachers, let's pick up with section 12-2. In 12-2 we're going to talk about additional congruence theorems. In particular, we're going to talk about geometric constructions leading to the angle side angle and angle side congruence properties, along with examples for both of those cases, and we're going to talk about properties of quadrilaterals. Okay, so the first property we want to talk about today is the angle side angle, also known as ASA property. If two angles and the included side, so we're talking about the side between two angles of one triangle, are congruent to two angles and the included side of another triangle respectively, then the triangles are congruent. Notice what's pictured here is actually a construction. You can use angle side angle to copy a congruent angle or triangle of a known triangle. So we have this known triangle ABC, and we're trying to copy it over here in pink using the angle side angle property. So how could we do that? Well, first of all, you need a line drawn at the bottom. Okay, now let's reproduce our angle. So our first angle we want to reproduce is angle A primed over here, which is a copy of angle A. Do you remember how we could do that? So you can sit your corner right here on A and just draw an arc. Okay, so draw an arc. Now go and draw that same arc over here on your line. You need a line somewhere to start with. So let me back up here. Draw a line at the bottom. You don't have to copy A prime, C prime yet, but just draw a line, okay? And then come and mark over here, okay? And then, again, mark over here. Now, you have to have a beginning point right here, A primed. Now, the next thing you're going to do is put your point of your compass here and measure here. And then you will do the same thing, put your point of your compass here and measure here. Now, where those intersect, you draw a ray. Okay, so from your point A prime, you draw a ray. Then, so that's your first angle. Then you can do your side. Okay, so you know how to copy a line segment over. You just measure, put your corner here of your compass and your pencil here at C, and then copy that over here by putting an arc, and then you just draw your line segment on top of the line that you have already drawn. Okay, and now we want to draw angle C over here. So you come over here and you put your point of your compass on C, because you have a C primed over here, so put it on C. Again, just open up your compass, it doesn't matter, just not huge, not too small, and draw an arc. Then draw that same arc over here, okay, and come back, put your point here, and measure here, and draw an arc there. And again, where these intersect, you draw a ray from point C primed on, and those will automatically intersect at point B. So we used angle side angle to do a construction. Notice I didn't do the real construction, I just talked you through it so easily. I have left out an important detail. But don't forget, you can view videos of each type of construction. If you go to your Canvas course and select the construction videos, a list will pop up and you click on the video that you would like to see. Okay, so angle side. Notice we did angle side angle. There's also an angle side. So if two angles and a side opposite one of these two angles of a triangle are congruent to the two corresponding angles and the corresponding side in another triangle, then the two triangles are congruent. Notice we have a picture here. So we've got the angle. So we've got an angle of 70, oops. Let's get that pen working like it should be. An angle of 70 degrees here. That corresponds to E over here, that's 70 degrees. So B and E angles are congruent. And then you go on to angle A and angle D are congruent. And then you have a side. Notice the side is not between them. It's on the side associated with the 40 degrees. Now, anytime you're doing this, make sure the side you know is on the same side. So if 6 was over here, that doesn't cut it, right? The 6 length has to be next to the 40 degrees. And so this would use angle, angle, side to show congruence. Now this side says the same thing, angle, angle, side, but I have a question for you. Notice this diagram is different than the page I just had up. And I ask, are these triangles congruent? Can we use angle, angle, side or angle, side, angle to show that these two triangles are congruent? And you look real fast and you go, sure we can, right? We've got 75 degrees and 75 degrees, and we've got 60 degrees and 60 degrees, and this side matches this side. But do you see what the problem is? Okay, so we have, in this situation, we would have, I would say this is an angle, side, angle. But in this situation, we have angle, angle, side. Oops, I wrote that wrong. Angle, angle, side. So angle, angle. The side is not between the two angles like it is here. So something's got to give. You cannot show congruence in this particular situation. You've got to make sure the angles match up and the correct sides match up to show congruence. So be very careful with that. So we have example 5 here. Show that the triangles are congruent. So I would like to show that these triangles are congruent. So look at what information we have. So we have an angle, okay, of 70 degrees, and we have ABD. Let's write that down. So we're trying to show, remember in the last section we got good at writing this down. So I'm trying to show that angle ABD, or triangle ABD, is congruent to the other triangle. Now, we don't even know how to name it yet. Okay, so stand by on that. But what do we notice is the same? So we could say we do see that angle ABD. I can't call that angle B, right? Because it's split up into two different angles. So angle ABD is congruent, okay, to angle, how about we call that CBD? Because they are both 70 degrees. Okay, so that's an angle. Notice we have a side right here in the middle that definitely matches because it's the same side for both of them. So I'm going to say that line segment BD is congruent to line segment, now this is angle CBD, angle ABD. They both end at the bottom. The side should be BD, right? Nothing is flipped around. So we're going from ABD, CBD is what we've got going on. Now, what else do we have going on? This 50 degrees matches, right? So how do I want to name that? Let's call that angle BDA. That's not the only way to name it, by the way. And that would be congruent to angle. If I call that BDA, that would be BDC. All right. Now, let's label what we have. So this was an angle. This was a side. This was an angle. So we can say that triangle ABD is congruent to triangle. That would be CBD. Notice the order. CBD. It's still in that order, but you'd have to move that there. Okay, but it's still CBD. Okay. ABD is congruent to CBD by angle, side, angle. Now we want to check our work by just looking at the typed up version. And we have ABD is congruent to CBD by angle, side, angle. So their argument was exactly like ours, just not listed like we did it together. Now here's a second example 5. How about you pause the video and see if you can do this one on your own. Were you able to pull this off? So it's even hard to discern which one's which. So make sure you clearly see what's going on. I'm going to say we have triangle ABC. This is the one with the long line, and you could even make that black just to make it more clear to you. So if we look at triangle ABC, I'm trying to show that triangle, put this at the very bottom of the page, right? ABC is congruent to. We're not going to even write up what the other one is. Okay, let's just look at the facts, right? So we know that we have angle A, and we can name it BAC if you want to, but I'm just going to call it angle A. So angle A is congruent. Is there another 30-degree angle? Sure is. That's up there at angle D. Okay, so we have an angle that matches. All right. Notice I'm looking back at ABC. If I go in order, A, B, look, angle B corresponds to angle E. They're both the same size because they're 90-degree angles, right? So I'm going to say angle B is congruent to angle E. Again, because they're both 90-degree angles. They have the box in there. So we're confident that those match. And then do we know a side? Okay. Well, I'll argue we do. So we have an angle. Let's look at our long ways triangle. Okay, our black triangle here. Again, if it helps, you could draw over that in black. They've got it drawn over in pink where you might see that better. But let's just look at our black triangle. Okay, ABC. We notice that we have a length of 5. So we can say that line segment BC, trying to get my color back. So line segment BC is congruent to, do we have a corresponding BC? How about EC? Now, why didn't I say CE? Because C was the corner on this one. So if I go, the corresponding B over here is E. So BC corresponds to EC, or they are congruent because BC and EC are the same length line segments. Okay, now is that enough? Is everything located in the same place for both of them? And I would argue that it is. The angle 30 degrees, okay. Look at the hypotenuse. That's that long side. We weren't discussing the hypotenuse. We were discussing one of the legs was 3 and a leg over here was 3. Okay, so how do we write this out? Triangle ABC corresponds to, remember the A was at the 30 degrees, so that would be DEC. And that's even how we have it listed, DEC. Are you convinced? Well, what did we use to show that? Okay, so let's do our list. That's angle, side. If you'll notice this time, the side that we knew was not between the two angles. We knew an angle, and then we knew that side. It is not the side in between. So we could say this is true by angle, side. Now, we look up at their typed up version, and you have ABC corresponds to DEC by angle, side. Now, what I want you to think about right now, maybe we'll just write it on this page. I'm going to review it at the end of this video because I want it to be very, very clear. But what do we know to prove triangles congruent? Well, in the last section, we worked with side, remember? And we did side, angle, side. We discussed side, angle and said, nope, that's not going to work out. Right? Because it's not enough to show congruence. There are reasons. I will discuss those shortly. We also marked out the idea of angle. Again, those are both going to be discussed at the end of the video, so just hang tight. But I want you to be aware of what we could use. That's not all of them, right? Today we did angle, side, and angle, side, angle. Is that every single possibility of what could happen? You could rearrange some of the letters, but that's going to give you the same situation. And be careful rearranging some of them. Like the one that we can't do. Don't move that around too much. Okay? That's how I remember it's one you can't do, if that helps you at all. It kind of helps me. All right, so let's talk about some other things. Okay, so for the next example, we're going to do a proof. Okay, so it says using the definition of a parallelogram and the property that opposite sides in a parallelogram are congruent, we're supposed to prove that the diagonals of a parallelogram bisect each other. And that's going to end up on a list of things we know about parallelograms. But hang tight, let's back up a little bit. Using the definition of a parallelogram. What's the definition of a parallelogram? Do you remember? So, definition of a parallelogram, that the opposite sides are parallel. So that means that BC is parallel to AD. So in other words, this guy is parallel to this guy. Okay, what else do we know? The opposite sides are parallel. So also I can say that AB on the left over there is parallel to DC. C. There we go. So I can point out also that this side is parallel to this side. That's the definition of a parallelogram. And then it says, and the property that opposite sides in a parallelogram are congruent. So that means they're the same length, right? So I could also say that this side is the same length as this side, and this side is the same length as that side. So these are things we know right now. What we're trying to show, though, is that the diagonals of the parallelogram bisect each other. Okay, so what does that mean? Bisect means they cut them in half, right? So you know what the diagonals are. From B to D is a diagonal, and from A to C is a diagonal. Okay, so we know that BO needs to be congruent to OD. That's what it means to bisect, is that you get equal lengths. Also, we're trying to show AO is congruent to OC. So once again, that's a bisect situation. So this is what we're trying to show in the end, that BO is congruent to OD and that AO is congruent to CO. Let's see if we can do that. Now to do this, what we're going to do is just follow along with the proof, and let's make sure we understand everything that's happening here. So we have line segment AD is congruent to line segment CB. Let's don't even read what it says. Let's find it. AD down here at the bottom is congruent, this guy right here, to CB. We already talked about that on the previous slide, right? So we're good to go. Because why? Again, because it's opposite sides of a parallelogram are congruent. They mentioned that when they set up the problem. Okay, now since AD is parallel to BC, we talked about that too. That's the definition of a parallelogram. Okay, follow me here. Then angle OAD. Let's find OAD. So angle OAD, okay, they've already got a mark there, here, is congruent to OCB. So OCB, this guy right here. Now notice they already have that marked. Why are they congruent? Because it just says since AD is parallel to BC, then angle OAD is congruent to OCB. Okay, how do we know that? All right, how about alternate interior angles? Right, so this is our transversal. I'm going to highlight that guy in green. This is our transversal that goes through our parallel lines. Okay, so again, BC is parallel to AD. Those are alternate interior angles. That's how we know they're equal to each other. Okay, let's keep reading this and see if we buy into their argument. So they've got these two labeled the same. All right, two angles. Okay, and angle ODA. Where's ODA? So ODA, okay, that's this guy right here. And angle OBC, so OBC, that's this guy right here. Notice they have matching arcs with the one line on it. Why are they congruent? Well, once again, that's alternate interior angles. Matter of fact, I'm not so impressed with their proof because they should be saying that. Okay, they should make every single thing clear. Okay, so now from that, they argue, I'm going to erase all my marks here, they argue that triangle OAD is congruent to triangle COB. So this is what I'm talking about right here. Okay, let's highlight it. Triangle OAD, that's this guy right here, is congruent to triangle COB. Are those two congruent? How would you argue that? So we know that this angle matches that angle and that angle matches that angle. That's our alternate interior stuff. Remember, I had it marked but got rid of it. This side and this side are congruent. They even restate it right here. Okay, so this is angle, side, angle. Angle, side, angle. So there we go. They did list that. That was by angle, side, angle. Okay. Now let's keep going. We'll see if we can follow what they're saying. They're saying line segment AO is congruent to line segment CO. Now let's find AO, and I'm going to erase again. Okay, so line segment AO, that's this one right here, is congruent to line segment CO. Now how would we possibly know that? Aha, they wrote it down, but this is terribly important. Once you have congruent triangles, any part of those triangles are congruent. And the way you name that is corresponding parts of congruent triangles are congruent. I can't say it. CP, corresponding parts of congruent triangles are congruent. I don't know if they put the T in there or not. I tend to say it every time and not write the acronym for it, and they wrote it this time. So corresponding parts of congruent triangles are congruent, okay? So once you know that, then you know, again, that AO is equal to CO. Not only that, BO over here, I'm going to highlight in green, is equal to DO, because corresponding parts of congruent triangles are congruent. I can't even say it. Now, is that what we were trying to prove? Remember what we were trying to prove? That the diagonals bisect each other, so that the greens are equal and the purples are equal. We proved it. We did it. Okay. Basically, we just followed the proof and explained why everything is what it is, but that is still understanding the proof, and that's what we want to try to do right now. Okay, now let's spend some time talking about properties of quadrilaterals. And may I warn you, there are a bunch of properties, and you're probably going to have to keep referring to some of these pages as you go through your homework. So first, let's start with trapezoids. Okay, so if we have a trapezoid, you see there's one depicted right here. Trapezoid is a quadrilateral with at least one pair of parallel sides. So what makes a trapezoid? A trapezoid, again, is this side and this side, and it could be sideways. They have parallel sides, one pair, okay, at least one pair. You could have two pair, which would make you have a what? Parallelogram, okay, but trapezoid doesn't have to have two pair. Consecutive angles between parallel sides are supplementary. What are they saying? What does that mean? What does supplementary mean? Adds to 180, yes. So it says consecutive angles. So this angle plus this angle, the sum is 180 degrees. All right. Now, let's look at a special type of trapezoid. So an isosceles trapezoid. What is an isosceles trapezoid? You still have the parallel sides because that's what trapezoid means. But isosceles means that your other two sides are the same length. Okay, so line segment BA is congruent to CD. Okay, now what does this mean outcome-wise? Well, each pair of base angles are congruent. So what are we trying to say? That this angle over here is equal to this angle over here. They have it marked just much smaller. Not only that, you could consider this is a base angle and this is a base angle as well. And since I marked all over it and I like the way it was marked originally, look at that. That's what we're saying. So these two bottom angles are congruent and the top angles are congruent. But keep in mind, that's only true for an isosceles trapezoid, not just any old trapezoid. Any old trapezoid has the parallel sides and the sum of the corresponding angles is 180 degrees. But isosceles trapezoid, each pair of base angles are congruent. A pair of opposite sides are congruent. Okay? So that's the definition of an isosceles trapezoid, by the way, is the opposite sides are congruent. That was their original definition. If a trapezoid has congruent diagonals, then it is isosceles. Now, don't let this burn you in the homework. It has to be a trapezoid. If a trapezoid has congruent, not if anything has congruent diagonals. If a specific trapezoid has congruent diagonals, it is isosceles. So if you're looking at it and you go, yeah, that's a trapezoid because I know that this is parallel to this, okay, and then it has congruent diagonals on top of that, then it is an isosceles. Now, what do they mean by congruent diagonals? So from here to here is the same length of line segment as from here to here. That's congruent diagonals. All right, let's continue our properties. How about a parallelogram? What in the world is a parallelogram? It's a quadrilateral in which each pair of opposite sides is parallel. We did a proof just a minute ago using that information, right? So BD is parallel to AC. In addition, though, because it's a parallelogram, because that would make it a trapezoid, wouldn't it? But because it's a parallelogram, BA is also parallel to DC. Okay, that makes it a special trapezoid, a parallelogram. Okay, now what's up with the parallelogram? Lots. A parallelogram has all the properties of a trapezoid. That's the first of all, because a parallelogram is a special type of trapezoid. Opposite sides are congruent. So what does that mean? Here, this length is equal to this length. Remember, we talked about that in that last proof. Opposite angles are congruent. Okay, so this angle is congruent to this angle. Not only that, this angle is congruent to this angle, and I forgot to mark this side is congruent to this side. That's a whole lot of property right there. Diagonals bisect each other. So if you draw the diagonals, they cut each other in half. Y'all, that's what we proved, right? This is exactly what we proved just a minute ago, so hopefully it'll stick in your head. But if I draw this diagonal from here to here, and this diagonal from here to here, what I know is, let's go with orange, this is all starting to look the same, that this length equals to this length, and on the other diagonal, this length equals that length. That's what bisect means, it cuts it in half. Okay, now, here's the good stuff. A quadrilateral in which the diagonals bisect each other is a parallelogram. So if you have a four-sided figure, and you know that the diagonals bisect each other, you have a parallelogram. Okay? So you read it two ways. If you have a parallelogram, the diagonals bisect each other. If you have a quadrilateral and the diagonals bisect each other, not dissect, it's a different class. The diagonals bisect each other, that's a parallelogram. All right, properties. Let's keep going. This time, we're still talking about properties of quadrilaterals. We're talking about a rectangle. Now, a rectangle is a parallelogram, so all of those properties that we just talked about with the parallelogram, and there are a lot, right? A rectangle has those, and then what's the extra? You got 90-degree angles going on in here. So we've known about rectangles for a long time. So a rectangle has all the properties of a parallelogram. You remember listing them in your head? Parallel sides across from each other. The length of BC is the same as AD, so they're congruent. BA is congruent to CD. The diagonals bisect each other. And now we're going to add that all the angles of a rectangle are right angles. All four of them, not just A over here, but all four of those. A quadrilateral in which all the angles are right angles is a rectangle. So back and forth. If you have a quadrilateral with all right angles, it's a rectangle. If you have a rectangle, then it's all right angles. The diagonals of a rectangle are congruent and bisect each other. Now notice that was not true for a parallelogram. They just bisect each other. They might be different lengths. But for a rectangle, the diagonals cut each side in half. Okay, so here and here and here and here, because it is a parallelogram, but they're actually the same lengths. Okay, does that not mean all four of those are the same? So should I even put the double marks, right? Wouldn't that not be that that and that are equal also? Okay, are congruent bisect each other. A quadrilateral in which the diagonals are congruent and bisect each other is a rectangle. So anytime you know you have a quadrilateral, you could show that the diagonals are congruent and they bisect each other, you know you have a rectangle. You don't even have to know that the corners are 90 degrees. As long as the diagonals are the same length, which they're congruent, and they bisect each other, then you have a rectangle. All right, let's talk about a kite now. And we've got two examples depicted here, a convex kite and a concave kite. But what's a kite in the first place? Well, a kite is a quadrilateral with two adjacent sides congruent, and the other two sides are also congruent. So if I use my fancy highlighter here in green, again, this side's congruent to this side. They're adjacent because they're touching each other. And in addition, this side is congruent to this side. Again, adjacent sides. And even for the concave kite, that's still true. that notice that this side is the same length as this side, and then the other two adjacent sides are also the same length. That gives it symmetry, and it's shaped like a kite, even a fancy looking kite that we have here. Now, what do we know about kites? Well, lines containing the diagonals are perpendicular to each other. All right, so what does that mean? So check this out. If I draw a diagonal AC right here, and then the other diagonal DB right there, perpendicular. Okay, let's do it on this one also. So if I draw diagonal AC, now careful, that's going to have to keep going this way. And then the diagonal is outside, because this is a concave kite. The diagonal ends up being outside in this situation, but those things are still perpendicular to each other. Okay, a line containing one diagonal is a bisector of the other diagonal. Now, can you see which one is the bisector in our higher one here? It's certainly not this long one, right? Because to the right is longer than to the left, but we could argue probably that this length is the same as that length. That's what bisect means, right? And definitely not this line here, but this length is the same as this length over here, okay? One diagonal bisects non-consecutive angles. Now, what's an angle bisector? So that's what this is saying. One diagonal, here we go, bisects non-consecutive angles. So you're splitting the angle in half, right? It appears to me that this bisector here, the vertical one on the concave kite, the vertical one that's outside is certainly not bisecting those angles. But right here, that looks like, and here, that looks like it bisects those angles. And in this situation, that is just an appearance, but it appears to me that those are bisected by that diagonal, but not by the DB diagonal. Okay. Now, finally, a quadrilateral in which the line containing one diagonal is the perpendicular bisector of the other diagonal is a kite. So if you have a quadrilateral in which this situation is true, you absolutely have a kite. Okay. So again, one diagonal is the perpendicular bisector of the other one. That's how you could prove something is a kite. A quadrilateral. It has to be a quadrilateral, right? Okay, let's keep going. I'm going over my time, but I'm going to finish the properties before we come back to part 2 and do a lot of examples. On to a rhombus. A rhombus is a parallelogram. Remember what that means? That you've got two sets of parallel sides with two adjacent sides congruent. Okay, so two adjacent sides are congruent. So that's congruent to that, and then that one's congruent to that one. Now it says a rhombus has all properties of a parallelogram and a kite. So anything that's listed under parallelogram and anything that's listed under kite is a rhombus. You can see that it's a nice compact rhombus there, okay, because it's got parallel sides. A quadrilateral in which all the sides are congruent is a rhombus. So first it said two adjacent sides are congruent, but here it says all the sides are congruent, and that's why they have the single line over each of those. And why I went ahead and shaded all that in green. Okay, now the diagonals of a rhombus are perpendicular to and bisect each other. Okay, so the diagonals, there's a diagonal and there's a diagonal. They're saying they are perpendicular to each other, so that's a right angle right there, and all four of those are right angle, and they bisect each other. So this length and this length is the same, those are equal, and this length are equal. Okay, a quadrilateral in which the diagonals are perpendicular and bisect each other is a rhombus. Okay, if you have both of those situations, you know, and a quadrilateral, so three situations, you know you have a rhombus. And then one more set of properties, then I'm going to shut this down and we're going to come back for part 2 with a ton of examples. All right, a square. We know what a square is. It's a rectangle with all the sides congruent. All the sides are the same length, right? Not only that, it has 90-degree angles. So a square has all the properties of a parallelogram and a rectangle. That's what makes it have the 90-degree sides, okay, because rectangles have 90-degree angles too, not sides, angles, and a rhombus. So a parallelogram, a rectangle, and a rhombus. a rhombus with a right angle is a square, pretty much. So if you know you have a rhombus, which again, how do we prove we have a rhombus? Back over here, diagonals are perpendicular to and bisect each other is how you prove you have a rhombus. Well, if you have right angles in addition, you absolutely have a square. Okay, lots and lots of properties there. So you're going to find yourself sifting back through these to especially with the diagonals, I think you'll have to look at those properties very closely. All right, now I'm going to come back with some examples, and then we're going to call section 12-2 done. Let me know if you have questions, but come back for part 2 before you dig into the homework too deep.